Hello everyone, my name is Shang Yuwei. Today I'm going to talk about the influence of lighting conditions on the performance of CNN-based equipment load detection for energy demand estimation. According to the International Energy Agency report, the building sector accounts for 36% of global energy use and 39% of greenhouse gas emission. As the major energy consumers in the buildings, HVAC systems consumes over 40% of the total energy use. In the regions with hot climate, it could be over 50%. Due to the growth of global temperature, HVAC systems will consume more energy for cooling to maintain a comfortable indoor environment. There is also a large waste of energy used in buildings. The findings of the study carried out by University College London show that there is a remarkable difference between design and actual energy use in buildings. How can we improve it? One of the solutions is to design an optimized control system to achieve higher building energy efficiency. When designing HVAC system control strategies, equipment heat emission is an important factor as it is one of the main sources of internal heat gains. For office buildings, more electronic equipment will be installed and used. Commonly, we use a static schedule to design and operate HVAC controls, while the actual usage is stochastic and dynamic. So the use of typical schedule could cause a large waste of energy use and uncomfortable indoor environment. And in addition, there are only few studies attempting to predict the heat gains from equipment, so it is required to develop a system to better understand and even reduce the impact of internal gains from equipment. Currently, power meter, doing surveys, and analyzing occupants' behavior are the technologies used for equipment detection. But compared to the occupancy detection technologies, the methods for equipment usage detection are conventional and limited, so more developments are required. Camera is introduced to my project as images can contain a lot of information we need. In terms of this, deep learning and computer vision methods are used in this project. Compared with traditional machine learning, deep learning decreases the complexity and outperforms on recognition tasks with high accuracy. And to my knowledge, no work focused on using deep learning to detect comprehensive equipment information. There are different types of deep learning. Based on their common applications, CNN is selected to perform detection tasks in this project. But here comes a problem. When designing vision-related detection technology, illumination is important and necessary to be considered. Because of these factors, the lighting conditions of the scenes and the target may change greatly. Improper lighting conditions can cause poor detection performance of the proposed method. So this work aims to further develop the vision-based equipment load detection approach to detect and predict internal heat emission from equipment and investigate the impact of varying lighting conditions on the detection performance. Move on to the methodology. This is my proposed framework. It can be separated into two parts: detection model preparation and deployment of the model and energy assessment. The first part will be discussed later. In the second part, the proposed detection model is implemented in an actual office space to collect equipment usage data with the use of camera. The obtained data could then be inputted into the control system to automatically adjust the HVAC operation. In order to assess its flexibility and analyze its potential impact on building energy use, the data was inputted into a building energy simulation software to perform energy modeling. According to the results of energy performance, the ability of the proposed framework could be evaluated. Here is the workflow of the detection model preparation part. Python and TensorFlow object detection API were used to carry out this workflow. The faster RCNN is selected as the detection model, then a large number of images of office space is collected and randomly divided into training and testing dataset with the ratio of 4:1. After labeling both training and testing dataset and finishing training preparation, the model is trained and tested with the dataset and further optimized based on the detection performance. Then it is implemented for real-world detection. To test the framework, an experiment was carried out in the Open Plan Office in Sustainable Research Building at the University of Nottingham. Here shows the setup of the experiment. Within the detectable range, there are 8 monitors and each monitor is connected with the desktop computer. The equipment usage information was gathered for the whole typical workday. To evaluate the impact of lighting levels, 12 scenarios were designed in terms of the different time of a day, various day lighting and artificial lighting conditions, and shown in this table. To assess the effect of using proposed model on the energy performance, the equipment load profile created based on collected data was inputted into the energy simulation software to simulate the energy demand and compare with the energy performance of using typical profile. Let's see the results. According to the test results, the actual equipment heat emission profile was generated as shown here. The daily heat gains obtained by deep learning detection model was much less than the heat gains with typical schedule in total. Compared to the typical heat gains profile, the result of the deep learning-based profile shows the variations in equipment usage corresponding to the specific time of the day. Here are some examples of results at different times. It implies that applying deep learning-based profile to the HVAC control system may be highly possible to meet the real-time requirements. However, through the comparison between real-world observation and deep learning detection results, there is still a number of obvious errors. So further optimization must be carried out to reduce error rate in the future work. After carrying out the energy simulation, you can see the results of total cooling loads during the cooling season based on the typical and deep learning-based profiles. It indicates that up to 15% reduction of cooling energy was predicted to be achieved by using deep learning-based profile. It highlights that the deep learning approach for equipment detection could affect the energy use by making HVAC adapt to actual energy demands in real time. To investigate the impact of lighting levels, 12 scenarios were carried out as shown here. It indicates that the trained detection model has the ability to identify the desired object under different lighting conditions with relatively high accuracy. This graph plots the illumination at the measuring point under different detection scenarios and time of the day. The table lists the results of detection performance under different lighting levels. The average value of F1 score indicates that the selected detection model can handle the equipment detection and recognition task excellently. By comparing the figure and table, it can be observed that different lighting conditions affect the performance of detection tasks. At daytime, higher lighting levels around the desired object could achieve a better detection performance, while at nighttime, the selected model performed better under a dimming lighting. To improve the detection model to adapt to different lighting conditions, it's necessary to collect sufficient training data of various lighting scenarios for the desired objects. So in this study, a vision-based equipment load detection approach to detect and predict internal heat emission from equipment was further developed, and the impact of lighting conditions on detection performance was investigated. To achieve this, data collection and the training of proposed model were carried out. An experiment was conducted and the findings showed that up to 15% reduction in energy consumption for space cooling could be achieved. It also highlights that the proposed model is able to identify the desired object under different lighting conditions with a relatively high accuracy. To improve the proposed method, more images are required to be added in the dataset. Further development is necessary to get a better detection model which can streamline the real-time data from output of the model to the HVAC control system. Also explore other object detection models. An investigation of the capability and feasibility of the proposed approach in an office conditioned by the HVAC system is required. So the future works can be demonstrated as this figure. That's the end of my presentation. Thanks for your attention.